Hello, a warm welcome to everyone. My name is Noor and I'm the product manager for electromagnetic applications here at SimScale. My focus is on making electromagnetic simulation accessible to engineers, helping them to innovate faster. That's an area closely tied to electric vehicle design as well, and that's why I'm here today. I would like to show you how cloud-native electromagnetic simulation and the artificial intelligence-driven workflows can significantly accelerate your design process. And here's what we'll cover today. After this introduction, I'll be sharing how we at SimScale empower automotive organizations through cloud-native multiple physics simulations. And next, I'll present two demos. In the first one, I will showcase a design study using our electromagnetic solver. And after that, I want to discuss how artificial intelligence enhances engineering simulations. And then we'll wrap things up with some key takeaways and summary of the session. And finally, we'll have a Q&A where I'll be happy to address your questions as well. All right, let's start by looking at some of the biggest challenges our automotive customers are facing today. And I'd be curious to know if these resonate with your experiences as well. So the most common pain points we hear include the shrinking development cycles. So they used to be around 24 months and now they're expected in 12 months or less. And the RFQ deadlines are getting tighter, dropping from several months to just a few weeks. And there's this race to local certification where companies compete to be the first to market. And OEMs are expecting highly engineered products, even at the RFQ stage, adding more pressure to design teams. In short, these factors put a significant strain on engineering workflows, and the only way to manage this increasing demand is by accelerating engineering processes, but of course without losing control over quality. And while simulation and AI won't solve every challenge, they play a crucial role in streamlining design iterations as early as possible in the design process. But of course, this relies also on one critical factor, which is making simulation results available at the early design stages, and that's unfortunately not often so common today. So let's explore why by looking at traditional simulation workflows. So in a typical engineering organization, simulations are handled by a specialized team, and the workflow looks like a designer creating a new model. Let's take, for example, the axial flux motor shown here in this case, and then the design is passed to the simulation team for analysis. Then there's this waiting period between requesting and receiving results is what we call simulation lead time. And now within this lead time, the actual simulation cycle time, which includes setting up the physics, meshing, and then running the simulation and sending back the results, is actually only a small fraction of the delay. But then why is that? That's because simulation teams are serving multiple departments and often have a backlog of requests, which means designers need to wait for days, if not weeks, to receive results before they can refine their design further. But now imagine a scenario where designers could access simulation results instantly without waiting for weeks. Then the entire design optimization process will be speeding up dramatically. So let's take a closer look at the limitations of traditional simulation setups that block these changes. Traditional simulation stacks were designed primarily for manual interaction and a centralized validation, rather than for automation or widespread accessibility. And that's exactly the structure we just discussed in terms of how simulation teams operate as well. And historically, when companies introduced simulation into their workflows, the process typically started with them investing in a CAE tool and together with that purchasing a workstation to run it, then adding some pre-processing tools and additional solvers for multiple physics simulation, and then building computing clusters to handle the increasing demand for simulations. Then the internal team started to write scripts to connect these tools and optimize the workflows. And as simulation needs grew, some companies also integrated early stage simulation into CAD, the CAE tools for designers. And in the recent years, some organizations have leveraged cloud infrastructure by adopting infrastructure as a service solutions, but the simulation lead time still stretch from weeks to days only. And our goal at SimScale is to bring simulation lead time down from days to hours and even to seconds. And one key enabler of this transformation is the cloud-native simulation technology. And why? Because cloud-native simulation stacks are built for broad accessibility across engineering teams, because That way you can focus on centralized data management, ensuring all team members can access results instantly. And the integrated high-performance computing can offer scalable computing power on demand. And there's seamless process management, actually, covering everything from user permissions to analytics. And then there's best-in-class simulation methods provided. They're flexibly integrated into an intuitive environment. And for industries like automotive and electric vehicle development, multiple physics are critical as well because engineers need to evaluate structural integrity, also working on cooling strategies and taking care of electromagnetic behavior from the earliest design stages. And the cloud native simulation can unify all these aspects in a single web-based platform, so the need to learn multiple tools could be eliminated. And on top of that, the infrastructure is accessible via a web API, and that allows organizations to automate workflows and integrate seamlessly with existing tool stacks as well. And by removing bottlenecks, this approach reduces simulation turnaround times from weeks to mere seconds, and that's something I'll demonstrate in the live demo shortly as well. But before diving into the platform demo, let's introduce SimScale for those who may not be familiar with us. So our mission is simple. We would like to empower engineering teams to innovate faster by making simulation truly accessible at any scale. And this covers like the first engineering simulation to be truly accessible at any place and at any time. And this is about engineers in your organization being able to judge the results, but that also covers being accessible to the experts at SimScale. And the live support we provide is something very important for our platform. And we've been also recently rated by G2 as the easiest to use simulation and CAE software. And you can see some of our customer logos that are already using SimScale and being supported by our support team to reach their simulation goals. So achieving our mission is possible through some main capabilities that we have. So first of all, engineers have access to both simulation data and the solvers, but also the expert support in real time with live support. And at SimScale, we can deliver simulation at any scale, allowing engineer teams to run simulations instantly in two key ways. So either through accelerating complex simulations, but also running unlimited simulations in parallel. Also, our multiple physics capabilities are empowering engineers to work with multiple physics within a single platform. So there is no need to switch between tools. Plus, our cloud-native infrastructure ensures that there is no need for remote desktop setups and also no on-premise hardware dependencies. And SimScale is cost-effective. So you can start with SimScale as you wish. You can start with one user or one team and then make it available to more teams or for all of your organization, just as you wish. And there's centralized data storage. So all simulation data is securely stored and instantly available. And that makes it ideal for AI-driven workflows as well. So what we provide in the platform is running the partial differential equations in parallel. And the moment these simulations are completed, they are actually ready for AI training. So here you can see as an example a structural study for the stresses on the bracket with different geometric variations. But of course, it's also possible to provide different simulation setup in addition to the geometric variations. And that's why cloud-native simulation is the perfect foundation for AI-driven physics modeling, because first, there is instant scalability provided. Second, there's seamless data accessibility. And third, the powerful AI integration in the cloud. Okay, so now in a bit, I will start with the product demo where I'll demonstrate how we can leverage a cloud-native simulation and what it truly means to have all physics accessible within a single environment. So we'll explore design optimization for a permanent magnet axial flux motor, and then we'll see how AI-driven simulation works in action. So the axial flux permanent magnets motors or machines are ideal for EVs due to their high power density and efficiency, but the rare earth magnets are costly. So optimization of magnet shape, their alignment, and also how they are arranged within the motor can enhance performance while reducing the costs. And using cloud-native simulation, we can quickly test multiple magnet shapes. In this case, for today's application, I picked 4 shapes, which are circular, semicircular, trapezoidal, and rectangular, to find the best balance of efficiency and, as a result, the cost of the motor at the end. And after that, we will also see comparison of different magnet materials and how they can impact the performance as well. And to do this now, I will switch from my presentation to the platform, and for that I'm typing simscale.com, and here you will land to the main page. So I will just go to my dashboard. Dashboard is where I can see all the projects I've been working on, or that my colleagues shared with me and I have access to. And sometimes I just store these simulations in separate folders to keep track of everything easily, as you can see on top. So here is my axial flux motor that I would like to show today. And here I have the 8 magnet circular version of my model. But as you can see, I uploaded 31 models by using OnShape API and also SimScale API. So as I parameterize my CAD models, I just through one click started to import everything to SimScale. And as you can see, there are also multiple simulations for different geometries, but also different material properties. I also started them with just one click by using SimScale API and running all of these in parallel. Okay, so let's find under my geometries this model I use, which is circular 8 air. So one thing to note, if when you're trying to get your model ready to be simulated, we also have some CAD editing capabilities in the platform directly. So if you click on this edit a copy button, then you will be able to start adding some details that are important for simulation. In this case, for example, I created this air domain surrounding all the solids you see here. And when you click on create simulation button, you'll see all the physics and all the solvers related to these physics listed here. And for today, and this is actually what is meant by multiple physics in a single platform. And because rest of the simulation running process is exactly the same for every and each of these. And today I would like to focus on electromagnetic analysis. That's why I click on create simulation, and here you can pick your model. Today we'll be simulating in using magnetostatics. And here I created a project for showcasing today. So I will continue the simulation tree I have here. And as you can see, there are some green icons, there are some red icons. These are also leading the user to for the steps to follow, so that it's ensured that the simulation is ready to go. So, for example, I have this material created here, but there were no bodies selected. So that's what I will do. I will assign the remaining magnets for this material here, and direction is already given with remanence and magnetic relative magnetic permeability. So this is ready to go. And for the rotor steel bases, I will be using the steel material. And as you can see, I also uploaded a BH curve, and I can also show it in a graph, so I can make sure that, okay, this is the material, this is the BH curve I want to utilize in my simulation. And I would like to also show you, okay, I will pick the volumes here. I would like to also show you the very extensive electromagnetic material database that we have. So as you can see, there are many permanent magnets or other materials that are important for electromagnetic analysis already provided in the default material library. And next step is to assign the coils. So I have already 3 phases, and 2 of them are defined. So I will go ahead with the phase B now, which are these coils here. And I pick topology as closed, but I can also pick open. So as I pick the closed topology, now I will also pick the internal ports, which means it will be shared by these 2 coil bodies that are in contact. And the coil type could be also selected as stranded, solid, or lit. But in this case, I will go with stranded. And actually, that's more or less all. So if you're also interested in calculation of inductances, you can toggle this on. Then you'll receive a table at the end of your analysis for the inductances. And if you're interested in electromagnetic forces and torques, you can also assign volumes here directly. And again, as a table at the end of your analysis, this will be provided. And now my simulation is ready to go. I can just start it here. All right, now let's check some of the results by running the study that I got. So first we analyze how different permanent magnet shapes affect torque production under identical three-phase current excitations. So the results are showing that magnet shape is directly impacting flux distribution and rotor field interaction. That's why we see these difference for different shapes. And that leads to significant torque differences. So as we can see, best performing one was circular magnets because they were providing the most uniform flux distribution. So consistent interaction was ensured, which resulted in highest torque output. But the worst performance was from the trapezoidal magnets because they were performing poorly due to uneven field distribution and weak alignment with the rotating magnetic field. But our key takeaway from this study is that even with the same magnet volume, the shape optimization is crucial in axial flux machines because it's directly impacting torque generation and the overall performance. And in the second study, I focused on circular magnets only because they were the best performing ones based on the geometry study I had. And by keeping the total volume the same, I had two versions. I created 8 and 12 permanent magnet cases. So the key takeaway is that using 12 magnets significantly outperformed the 8 magnets due to better magnetic flux distribution and stronger wind-and interactions, and that leads to higher torque output as well. So what we can see here is the neodymium offers the highest torque, while the samarium cobalt could be a great alternative when high temperature stability is a concern. And the ferrite Y40 provides a decent performance at a lower cost, and the usage of it could be optimized further as well because it's not the worst. But what to avoid here is the alnico underperforming, and it isn't a viable choice in this case. So now the next question is, we generated the data, but how does an AI model within the simulation workflow, within the engineering workflow looks like in the platform? So earlier we discussed how SimScale's cloud-native infrastructure is providing a solid foundation for AI training. And because AI models thrive on data and our platform seamlessly collects all relevant data points from CAD models and their modifications to simulation setups, then meshing and the final results. This centralized approach allows us to aggregate this information for AI training on the GPUs. And currently, SimScale can support AI-powered resource prediction and AI-driven simulation, but we are also continuously advancing AI capabilities, of course. There are more to come. So what is planned next includes the pre-processing automation and some intelligent setup suggestions and automated design insights to assist in decision making. So now let's put this into the context of electric vehicle development. We generated data for electromagnetic analysis. Let's say we are optimizing a vehicle and we are different teams working on this design. So in electric vehicle systems, multiple engineering teams work on different aspects of vehicle performance. For example, the control engineers handle the braking systems, and electrical engineers are designing electric motors. And hydraulic engineers focus on pumps and valves for the cooling systems. And to achieve optimal vehicle performance, of course, these independently developed components must work together seamlessly. That's why for this demo, I wanted to shift our focus to hydraulic engineering, let's say. Specifically, we are designing an EV cooling system. And a key component here is the electric water pump, which can circulate coolant throughout the system. And that's why we'll look at a centrifugal pump model. And traditionally running a full CFD simulation for this pump was taking 30 minutes to complete. However, with an AI-trained model, we can achieve instantaneous predictions for velocity and the pressure fields, so significantly speeding up the design process. And I will talk briefly about how we built this AI model. So this was a parametric study that was conducted by modifying design features like blade thickness, blade radius, and the diffuser length. And total of 180 design variants were simulated in parallel, generating a training dataset just within 2 hours. And this dataset was fed into an AI model, which can now provide instant predictions of velocity and pressure fields. And the model's accuracy reached 99% for pressure predictions, ensuring highly reliable results. And what makes this AI model powerful is its ability to generalize. And in the second demo, I will apply to a new unseen centrifugal pump geometry. So a model that was not trained for this AI model. And even though this design was not part of the training dataset, the AI model will still deliver highly accurate pressure and velocity predictions just within seconds. All right, so that's why I will jump into again to the platform. And as you can see, this is a centrifugal pump, one of the versions, but was not used for AI training. With 10 blades, and there is some. Sorry, here I can show there was some flow rate given through this phase. So what I need to do is there's this AI preview button here, and I click on radial pump model because that was the model we trained before for this centrifugal pump versions. And here what I see is the pressure being predicted just within seconds. And as we see, there's this range of AI model confidence being very high for this never seen model. All right. So, so this ability to predict complex physics in real time, of course, opens up entirely new possibilities for engineering teams because it can allow them to explore more design options and optimize performance faster and make informed decisions with confidence. So to wrap things up, today we explored how cloud-native simulation is transforming the simulation landscape and why SimScale is uniquely positioned to drive AI-powered modeling forward. We started by examining how parallel simulation workflows enabled via API-driven automation work, for example, for like large-scale design studies like the axial flux motor optimization we had. And then we saw AI-driven simulation in action through the centrifugal pump use case, demonstrating instantaneous physics predictions for an electric vehicle cooling strategy. And this slide also highlights other AI-driven applications in engineering simulation, because there are more opportunities. So it could be instant result preview, providing immediate design insights based on a vast data set of generic simulation models without requiring a dedicated AI training process. And AI-enhanced design automation is another. So it helps optimizing configurations, reducing manual effort, and accelerating iterations. And smart setup and pre-processing. AI can assist in automating model setup and making intelligent recommendations to the engineers. So what we understand is the role of AI in engineering simulation is still evolving and it's going fast. While its technical potential is enormous, the real impact will be determined by how organizations can successfully integrate it. And as the industry moves forward, we believe that the ability to effectively deploy AI in the simulation workflows will be the key differentiator for the engineering teams. And if your team is exploring AI adoption in your engineering workflows, we'd be really excited to collaborate and support you on that journey. So please just reach out. And thank you for your time and interest today. I'm now happy to take any questions.